Hi, in this presentation, we're going to discuss Newton's first law, and we're also going to talk about linear motion. So, in the 1500s, a scientist named Galileo challenged some old notions of motion. Um, uh, some of these notions were, for instance, people thought that if you had two spheres of equal diameter, and one was made out of iron and one was made out of a lightweight material such as balsa wood, if you dropped these spheres from the same height, the heavier iron sphere would hit the ground first. But Galileo did some experimentations and he found that objects of different weight are going to fall to the ground at the same time if there's no air resistance. He also found that a moving object doesn't need a force to be acting on it to keep it moving if there's no friction to slow it down. Galileo called this principle that he had observed inertia. And inertia is a property of all matter to resist changes in motion. And the amount of inertia an object has depends on how much matter or mass it has. Galileo also did some experiments with balls on sloping planes, and he found that if he rolled a ball down a downward sloping plane, that it started increasing its speed. It picked up speed. If he rolled the ball up an upward sloping plane, however, the ball went slower. It lost speed. And then when he rolled a ball on a plane with no slope, he noticed that it really didn't change speed. The ball would come to rest after a while, but that was due to friction, not to anything in the ball itself. If we could roll a ball on a perfectly flat plane with no friction and no air resistance, the ball would literally roll forever. It's important to remember when we're talking about inertia, it's not an outside force that acts on matter or a reason for the observed behavior of matter. It's actually a property of matter, just like taking up space is a property of matter or things that have mass. So it's intrinsic in matter. It's not something outside of matter that's acting on it. About 100 years later, after Galileo, Sir Isaac Newton reviewed Galileo's concepts and experiments, and he kind of refined the concept of inertia and wrote his first law of motion, which states that every object continues in a state of rest or of a uniform speed in a straight line unless acted upon by a non zero net force. So, in the absence of friction or air resistance, an object is going to keep on moving at the same speed until something acts on it. Or if an object's at rest, it's going to remain at rest until we have a non-zero net force acting on it. So when we talk about forces, what are we talking about? We're actually talking about any push or pull that acts on an object. So like the force of gravity, or um, if you actually are pushing a cart, you're exerting a force on it. And the unit of measure for force is the Newton, and we abbreviate that with a capital N. And a net force, when we talk about net force, we're looking at all the forces that act on the object and we're finding out what the final force is going to be. So let's look at the top of this picture here. And we have two 5 Newton pulls pulling the box towards the right of our screen. And we can add those pulls together and get a net force of 10 newtons going to the right. But let's say we move one of those forces to the opposite side, and now we have 5 newtons pulling the box to the right, but 5 newtons pulling the box to the left in the opposite direction. The forces are going to cancel each other out, and the net force is going to be zero, so the box is not going to move. So let's say we have a cart, and I'm pulling it with a force of 15 newtons to the right, but you think it should go to the left, and you're pulling on the cart with a force of 20 newtons to the left. What would you say would be the net force on the cart? Well, you're pulling with a greater force than I am, so the cart's going to move to the left. And if we subtract 15 from 20, we get a remainder of 5 newtons. So the net force on the cart is going to be 5 newtons to the left. Let's look at this box. if we're pulling with a force of 10 newtons to the right of the screen and then 15 newtons to the left of the screen, what would be the net force? Again, the 10 newtons is the greater force, so we know it's going to be moving to the right. And we can subtract the 5 from the 10, and we get a net force of 5 newtons to the right. When we're talking about force, we're talking about vector quantity. And a vector quantity is anything that has magnitude and direction. So forces, we're talking about the magnitude, how many newtons of force we're applying. And on our previous problems, we said we're pulling right or left, giving it a direction. Things like velocity and acceleration are also vector quantities, and we'll be talking about them later in this presentation. When we're drawing problems on paper or maybe in presentations like this one, we can represent vector quantities with arrows. And the point of the arrow tells us which direction it's going in. And the length of the arrow conventionally tells us the magnitude of that vector. So let's look at our little red car here. If we're driving forward, then the vector arrow on the right would represent our velocity. It would say we're going in this direction, and the magnitude of the arrow, the length of the arrow, tells us we're going pretty fast. But let's say we want to go in reverse towards the left of the screen. Well, most cars don't go as fast in reverse as they do forward. So the point of the arrow is going to say we're going towards the left, but you can notice the arrow is smaller. Our magnitude is less. So the arrow is going to be shorter. We also have what are called scalar quantities. And scalar quantities differ from vectors in that they only have magnitude. So we're not going to describe their direction at all. So things like mass, we can say this has 5 kilos of mass, and that's a scalar because it's not telling us anything about the movement of that object. Volume, I have a liter of Pepsi. Or even speed. Say you're driving in your car and you look down the speedometer, it says you're going 100 kilometers per hour. Well, that gives us a magnitude of how fast you're going, but it tells us nothing when you look at your speedometer about whether you're going north, south, east, or west. So speed is a scalar. So in our previous problems, we talked about vectors that are going in the same direction or opposite directions. And when we got our net force, we were actually getting what we call a resultant. Okay? And if a resultant is just the sum of two or more vectors. And for vectors in the same direction, just like the problems we did before, we add them together. So if we have a force of 2 newtons left and a force of 6 newtons left acting on an object, the net force on that object is going to be, or the resultant, is going to be 8 newtons left. For vectors in opposite directions, we just subtract the vectors. So if we have a force of 2 newtons left and 6 newtons right, then we can subtract the 2 from the 6 and get a net force, a resultant of 4 newtons to the right. But what if the forces are not parallel? What if they're not pulling in the same direction and they're not pulling in opposite directions? In this case, we have to use the parallelogram rule or a restatement of our Pythagorean theorem. That's a hard word. And basically, the parallelogram rule says our resultant r squared is going to equal one of our vectors, and we'll say the vertical vector in this case is x squared, plus our horizontal vector in this case, y squared. So if we square the x, the vertical vector, square the y, the horizontal vector, that and add those together, we will get our resultant squared. But then again, that resultant is squared, so we'll have to do a square root calculation to find what the actual resultant is on the object. So let's look at this picture. So we have a 30 Newton force pulling vertically, a 40 Newton force pulling horizontally. So let's square our vertical force first. So we have 30 Newtons times 30 Newtons will be 900. Our horizontal vector is 40 Newtons, so we'll square 40. 40 times 40 is 1600. Add those together and we get 2500. And then to find our final resultant, we'll do a square root of that sum, and the square root of 2,500 is 50. So we can see that our final resultant of the forces acting on this box is going to be 50 newtons. We can also use the same process to determine which of the vectors acting on an object is the greatest. So let's look at Nellie hanging from her rope here. There's three forces acting on her. There's her weight, which is her mass times force of gravity pulling her down. There's a tension in that long left hand rope, and then there's a tension on that short right hand rope. Because of the different angles of the rope, each of these ropes is going to have a different tension. The vectors are not going to be equal. Now, she's hanging in equilibrium, she's not moving up or down. So we know that the tension of the two ropes have to equal her weight. And we can see that in the drawing where the vector demonstrated by the dotted line equals the resultant of the two vectors holding her up. And then the solid line is the weight of gravity pulling her down. Okay. So we can compare the tension of the two ropes to our two vectors on the box we looked at earlier. So we can use the parallelogram rule. And so we can start at the point of our dotted line vector and then draw lines going out to each of our other two vectors that are parallel with those vectors and make our little parallelogram there. And then we can see in the last picture there how that demonstrates that the vector on the left-hand side is much smaller than the vector on the right-hand side. So that tells us the tension on the right-hand side of the right-hand rope is much greater than that on the left-hand side. So we notice that Nellie is hanging, she's not going up and she's not going down. She's in equilibrium. And that's what we call when the sum of vector forces acting on an object equals zero. That object is in equilibrium. So the tension on the ropes pulls Nellie up, gravity pulls her down, but those forces are equal, so she's just kind of hanging there in midair. We can write this rule as an equation. We can write the sum of, which is that Greek sigma symbol there, forces equals zero. And that's basically our equilibrium rule, that if the forces on an object equals zero, that object is in equilibrium. Let's look at our painters and their scaffold here. So let's say the scaffold, the force of gravity exerts a force of 100 newtons down on the scaffold. The painter on the left exerting a force of 200 newtons down. Painter on the right, he's a little thinner, 100 newtons down. And then there's two ropes holding up the scaffold. The one on the left has a tension of 250 newtons up. So what does the force on the right hand side have to be, that right rope? And we can do this mathematically, knowing that the forces have to equal out for the scaffold to be in equilibrium. So we can add the weight of the two painters in the scaffold, so that's 200 plus 100 plus 100. And we know that number is going to have to equal 250 newtons, which is the tension on the left rope rather, and then X, because we don't know what the tension is on the right rope yet. So we'll have 400, which is 200, 100, 100, equals 250 plus X. And then to find X, we just have to subtract 250 from each side of the equation, and we get X, the right-hand rope, has to have 150 newtons worth of tension. So we've talked about equilibrium in things hanging from ropes under tension, but we can also have things in equilibrium that aren't hanging from ropes or anything like that, but are just maybe sitting on a table. So think about if you put a book or a cup of coffee on a table, the, the book pushes down on the table pushes back up on the book to support it. We call that the support force. And sometimes you also hear it called the normal force. And the way this happens is as the book is pulled down onto the table by the force of gravity, it compresses atoms in the table, and those compressed atoms push back on the book. You can kind of think of this acting like when you push down on a spring. If you have a spring and you push down on it with your hand, you can feel the spring pushing back up. And the same thing happens when the book pushes down on the table. The atoms in the table push back up onto the book. So when we have a book on a table that's not moving, or we have a person hanging from a rope that's not moving, we know they're in equilibrium. The sum of the forces acting on them are zero. So we can call that static equilibrium. Something is still. So think if you go to the hockey rink and there's a puck resting on the ice and it's just hanging out there still on the ice. So we can say that puck is in static equilibrium. But what if we have another puck that's sliding across the ice at a constant speed? It's not changing speed, it's not changing direction. Well, this puck that's sliding at that constant speed is also in equilibrium. It's in dynamic equilibrium. So we can have equilibrium both in objects at rest and in objects that are in motion. So we can have an equilibrium test, and this is where we look at an object to see if it undergoes a change in motion. Because if something's moving at a steady speed in a straight line, it's in equilibrium. Its motion isn't changing. Okay, so we can have um, this crate in a warehouse. If the crate is just sitting in the corner, not moving, it's in static equilibrium, no change in motion. But if the worker needs to take that crate from one side of the warehouse to the other and he's pushing it across the floor, if he's pushing it at a steady speed in a straight line, then also there's no change in motion because it's moving at the same speed in the same direction. So now it's in dynamic equilibrium. And we can see this because the sum of the forces acting on the crate, the worker's push versus the friction of the floor resisting that push, are in equilibrium. So, what do you think would happen if the worker started pushing harder? Well, then now the sum of the forces are not going to be zero. His push force is going to be greater, so the crate's going to speed up. So it's going to undergo a change in motion. And if his force is less than the friction, say as he's pushing it across the floor, it hits a area of carpet. So the friction's increased now. So now again, the forces are not in equilibrium. They're not, the sum of the forces is not zero. So we're going to have a change in motion. The crate's going to slow down. So it's no longer in dynamic equilibrium. So let's say you're pushing a crate at a steady speed in a straight line, and the force of friction resisting you is 75 newtons. So how much force do you have to apply to keep that crate moving at a steady speed? And of course, you have to apply a force that's equal to 75 newtons. If you apply more than 75 newtons of force, your crate's going to speed up. And so we're going to have a change in motion and it won't be in equilibrium. If you apply less than 75 newtons, the crate's going to slow down because now the force of friction is greater. And again, it's not going to be in equilibrium. But if our push 75 newtons equals a friction force 75 newtons, the crate's going to move at a steady speed. There's no change in motion, so it's in equilibrium. So thinking about this inertia and equilibrium, let's talk about Nikolai Copernicus, who was a scientist that observed the motions of objects in the heavens and proposed that the earth is moving. The sun is at the center of our solar system and that the earth is moving around the sun. And a lot of people at the time did not agree with this because they had been taught for hundreds of years that the earth was in the center of the universe and the sun and the moon and the planets and stars all revolved around us. So some of the problems that other scientists had with Copernicus's hypothesis was that they didn't understand inertia. So they didn't see that where the force could come from to keep the earth moving because they didn't understand about inertia that says there doesn't have to be a force to keep it moving. And also they calculated that to circle the sun, the earth would have to travel at a speed of over 100,000 kilometers per hour. And of course they were saying, well, we'd be falling off the earth if we were moving that fast. But I'm sure you can probably see why it is that even if the earth is moving fast, we don't fall off. And we can explain why we don't fall off the moving Earth by looking at another argument that some scientists tried to use against Copernicus. They said, well, let's consider there's a bird on a branch in a tree, and that bird sees an earthworm down there, and he says, ooh, that looks like great breakfast. I'm going to go get that worm. So they said in the second it takes the bird to swoop down from the branch to the ground, the Earth is going to move 30 kilometers in 1 second if Copernicus is correct. So obviously the bird's going to miss his breakfast by 30 kilometers, right? But that's not what happens. Inertia is the answer to this question because think about it, not only just the Earth is moving at 30 kilometers per second, but also everything on the Earth, the tree, the bird, the worm, and even the air in between them is all moving at the same speed. So when the bird jumps off the branch to go down to the worm, inertia keeps him moving at the same speed as the Earth, and he lands right on top of the worm. In thinking about this concept, think about if you're taking a plane trip across the country. And most commercial airliners move at a speed of 800 kilometers per hour at cruising altitude. And you're flipping a coin. And you flip that coin right up in the air. Where do you think that coin is going to land? Is it going to land behind you because the plane's moving so fast? Is it going to move ahead of you for some reason? Or in your hand? And of course, the answer is not only is the plane itself moving at 800 kilometers per hour, but you are, the coin is, the air, the seat, everything inside the plane is moving at that speed. So when you flip up a coin, it's just the same as if you flipped up a coin sitting in your desk, sitting in your chair at home. It's going to land right in your hand. So now let's move on to see how these laws can affect linear motion. So we talked about motion and the movement of the Earth, and basically everything in the universe is moving. Right now, as we saw before, we're moving at about 30 kilometers per second relative to the sun as we revolve around the sun. But if you could draw back and compare our motion to the center of our galaxy, the Milky Way, you would see that we're moving around the center of our galaxy at 220 kilometers per second, which is pretty fast. So motion is always relative to something else. We're moving again at 30 kilometers per second around the sun, but we don't feel that motion because relative to the earth, we're not moving. We're sitting here still on the face of the earth, so we don't feel that movement. Same thing, we don't feel the movement around the galaxy because our whole solar system is moving that fast. So when we talk about motion, we can talk about speed. And speed is just the distance covered divided by the amount of travel time. And in physics, we measure speed in meters per second. And if we wanted to write a speed in an equation, it's pretty simple. It's just speed is distance divided by time. And when we do this equation, we also call this instantaneous speed. So instantaneous speed is your speed at any instant in time. So think about this. If you are going to take a trip in your car, and at some points in the trip, you might be going 100 kilometers per hour on the interstate. But when you started your trip pulling out of the driveway, were you going 100 kilometers per hour? Probably not. You were probably only going like 5 or 10. But every time you look down at the speedometer, it'll tell you, like if you're on the interstate, it might say 100 kilometers per hour. If you're driving through a residential neighborhood, it might say 30 kilometers per hour. So the speedometer is telling you your instantaneous speed, the speed right at that second. And if you've ever gotten a ticket from a police officer using the radar gun, that radar gun shot light rays to your car, bounced back off, and gave the police officer your instantaneous speed. And that's what you got a ticket for, was how fast you were going right at that instant. We can also calculate our average speed, which is the total distance covered, the total distance covered divided by the total travel time. And if we have an average speed, think about if I'm going to drive from here to Richmond, and it's about 60 miles, and it takes me an hour. So I can say 60 miles divided by 1 hour. my average speed was 60 miles an hour. But that doesn't tell me anything about my instantaneous speeds between my house and Richmond. For instance, again, when I left my driveway, I might have been going at 5 miles an hour. When I got on the interstate, maybe I was moving pretty quickly. Maybe I was going 75 miles an hour. And then if I was taking a back road, I might have had to stop for a stoplight. So I might have been 0 miles an hour. And those are various instantaneous speeds I could have had along the way. But that average speed was my total mileage, 60 miles, divided by the time, 1 hour. So my average speed was 60 miles an hour. We can look at this another way. Look at Usain Bolt running a 100-meter dash. He has a world record for the 100-meter dash, 9.58 seconds. And our average speed, if we calculate it out, his average speed for that 100-meter dash was 10.44 meters per second, which, to give you an idea how fast that is, a good sprinting speed for an athlete is about 7.5 seconds. So he's pretty fast. But think about Usain running this 100-meter dash. Did he come out of the blocks running 10.44 meters per second? Was he going 10.44 meters per second as he crossed the finish line? Probably not, because sprinters in the 100-yard dash, they start from zero, pushing off the blocks, and they accelerate during the entire race. And most elite athletes in the 100-meter dash are still accelerating when they cross the finish line. So at some points during that race, Usain's instantaneous speed might have only been like 2 meters per second. And then a little bit later, it might have been 8 meters per second. And at the very end of the race, when he was going past the finish line, still accelerating, he might have been going 12 meters per second. So the average speed doesn't tell us very much about instantaneous speed. So think about if we drove 30 kilometers in 1 hour, that's probably the same as the average speed of driving about 60 kilometers in 2 hours. Okay. So again, average speed is just the total distance traveled divided by the total time. So speed is a scalar. Remember we talked about vectors and scalars. It only has magnitude. So when we talk about speed, again, I could say I traveled at 60 miles an hour, but my speed doesn't really tell you anything about where I was going, which direction. When we add a direction of travel to this magnitude, now we have velocity. And velocity is a vector because it has magnitude, how fast we're going, our speed, and also direction. So when you see velocity, you can consider that directed speed. So constant speed is a steady speed, either slowing up or slowing down. And a constant velocity is a constant speed, but also since velocity is a vector, it has to be constant direction. So we can only say something has a constant velocity if its speed and direction stay the same. Because velocity is a vector, if we change either one, magnitude or direction, our velocity is going to change. So if we speed up or slow down, velocity is going to change. If we turn left or right, velocity is going to change. And we call this change in velocity acceleration. And acceleration, again, involves a change in speed or a change in direction, or sometimes both. So think about driving your car and you step on the gas, you start going faster, you change your speed, that's acceleration. But suppose you're going around a curve, and even if you don't change your speed, you're changing your direction, so that's also acceleration. And you can feel this happening if you're driving on a curvy road. And if you take a curve at the same speed, you can kind of feel yourself being pulled. Inertia is pulling you to the outside. It's because you changed your velocity, and inertia wants to keep you going at the same velocity. So if we wanted to write acceleration, which is just a change in velocity, in equation form, we would say our acceleration is going to equal the change in our velocity divided by the time interval. So let's take an example. Say a car's velocity is 40 kilometers per hour. And then 5 seconds later, its velocity is 45 kilometers per hour. So our change in velocity would be 40 minus 45. I'm sorry, 45 minus 40. That would equal 5 kilometers per hour. We can divide that by our time interval of 5 seconds, and we get an acceleration of 1 kilometer per hour per second. And you can write that 1 kilometer slash h times s. It's very important when you're doing acceleration equations, always remember to subtract your starting velocity from your ending velocity. So another way to write your acceleration equals change in velocity divided by time interval is acceleration is velocity 2, your ending velocity, minus velocity 1, your starting velocity, divided by the time. And we're going to see why that's important in just a second. So we know if we speed up our car, we've accelerated. If we go around a curve, we've changed direction, so we've accelerated. But what if we slam on the brakes and slow our car down? Well, that's a change in velocity, so that's acceleration too. Any change in direction or speed is acceleration. And when we talk about negative acceleration, we often call that deceleration. So let's think about deceleration. So let's say a cheetah is chasing a gazelle at 30 kilometers per hour. But the cheetah gets tired after about 10 seconds and his velocity drops to 10 kilometers per hour. So, what is his acceleration? So, always remember we're going to subtract our starting velocity from our ending velocity. So, we're going to subtract 30 kilometers per hour from 10 kilometers per hour, and we get a change in velocity of negative 20 kilometers per hour. And then we can divide that negative 20 kilometers per hour by 10 seconds, which is the time it took for the change to occur. And we get the cheetah's acceleration is negative 2 kilometers per hour per second. So we could say he was decelerating at the rate of 2 kilometers per hour per second. And that's why you can see it's important to subtract our um, starting velocity from our ending velocity, because if we don't, then we can make mistakes and maybe we'll think something decelerated when it accelerated, or vice versa. So always subtract your starting velocity from your ending velocity. So Galileo, while he was doing his experiments we talked about earlier, was experimenting with these inclined planes, and he found that the steeper the incline when he rolled his balls down them, the greater the acceleration, the faster the spheres rolled down the plane. And he noticed that once got the incline all the way up to vertical, then the spheres or balls could not roll any faster. Their acceleration was at maximum, and it was the same as just dropping an object in free fall. When air resistance is negligible, all objects, regardless of how massive they are, fall with the same unchanging acceleration. So, in the absence of air resistance, a bowling ball and a sheet of paper would fall with the same acceleration. There's a video at the link will take you to a YouTube video that demonstrates this in action, and it's a pretty interesting video. So I'll give you a few minutes to watch that, and then when you come back, we'll continue. So items fall because of gravity, and when nothing else is affecting the object, no friction, no air resistance like we saw in the video when they created the vacuum, the object's in free fall. On Earth, objects in free fall accelerate at 10 meters per second, or we can write that 10 meters per second squared. The precise measurement is 9.8 meters per second squared, but for the purposes of calculations in this class, I like to use 10 meters per second squared because it's easier to do the calculations and we can concentrate more on just the concepts. So knowing this about free fall, we can calculate the velocity acquired by any object that's in free fall from rest. And basically, its velocity is just going to be the acceleration that we determined before times the amount of time the object's been falling. So under free fall, the velocity of an object will be 10 meters per second after 1 second, because remember, our acceleration in Earth's gravity is 10 meters per second squared. The velocity will be 20 meters per second after 2 seconds, 30 meters per second after 3 seconds, and so on. So look at our picture here. We can say this person is dropping a rock off a cliff in free fall, no air resistance. So the the little speedometer shows us when it's in the person's hand right when they drop it, its velocity is 0. And then at 1 second, it's going to be 10 meters per second. It's going to be the velocity. At 2 seconds, it's going to be 10 meters per second squared times 2, so 20 meters per second. 3 seconds, it's going to be 10 meters per second squared times 3 seconds, so 30 meters per second. So let's say we have that object and it's falling at 30 meters per second in free fall. What would you predict its velocity is going to be exactly 2 seconds later? So the acceleration of the object is going to increase by 10 meters per second squared every second. So 2 seconds later, this object is going to have a velocity of 50 meters per second. So if we have objects moving straight up without any air resistance, they also slow at the rate of 10 meters per second squared. Because remember, deceleration is just negative acceleration. So now if we have an object moving straight up, it's moving against the force of gravity at the rate of 10 meters per second squared. So if you throw a ball up, it's going to decelerate 10 meters per second squared every second until at its highest point, its acceleration and instantaneous speed is 0. It's just going to kind of hang there for an instant. Then that ball will start moving downwards again as if you had dropped it from rest at that height. So if we throw the ball up, so we can see him throwing the ball up here, and it's going to decelerate 10 meters per second squared every second. So after 1 second, the ball has slowed from 20 meters per second squared to 10. After another second, it's slowed all the way to 0. And then after it stops accelerating, it will start coming back down as if we had just dropped it from this height. So after 3 seconds, it'll be moving, the velocity will be 10 meters per second. Then after 4 seconds, we'll add another 10 meters per second to 20 meters per second. We can also calculate the distance covered by an accelerating object from rest, and we can use this equation. So if we want to find the distance, it's going to be 1/2 of the acceleration times the time it's been falling squared. Okay, so 1/2 times acceleration times time. So under free fall, if we use our acceleration as 10 meters per second squared, the distance an object fell from rest would be 5 meters after 1 second, because we can multiply 1 times 1 times 10 is 10, and half of 10 is 5. After 2 seconds, the distance it fell would be 2 times 2 is 4, times 10 is 40. Half of that is 20 meters. After 3 seconds, 3 times 3 is 9, times 10 is 90, and 1/2 of 90 is 45 meters. So let's say, what is we have an object, we drop it. After 4 seconds, how far has this freely falling object gone? Okay. Do you think it's 4 meters, 16 meters, 40 meters, or 80 meters? Well, let's use our equation. Distance is 1/2 of our acceleration multiplied by the time squared. So distance is 1/2 of 10 times t squared. So it was falling for 4 seconds, so we'll multiply 4 times 4 and then multiply that times 10. 4 times 4 is 16, times 10 is 160, and then 1/2 of 160 is 80. So In 4 seconds, a free falling object would go 80 meters.